Welcome to Texas State University's Chemistry 2342, Organic Chemistry 2. I am your guide, Dr. David Irvin, and today we're going to start Chapter 15, Reactions of Aromatic Compounds, specifically the electrophilic addition aromatic substitution reactions. Okay, so what's important about us to look at this mechanism is used for most of the reactions in Chapter 15. So it's very important we understand it from its fundamental point of view. Okay, so the general concept here is that we have an electrophilic aromatic substitution. And in that, we have a hydrogen atom from the benzene gets replaced by an electrophile. Remember, the driving force in an aromatic compound is to maintain aromaticity. So substitution reactions are the most common reactions that we do that. And because of that, we keep the aromatic ring intact, okay? So this is probably the most important reaction we're gonna learn about benzene. Okay, so the generalized structure of the reaction goes where we have our benzene ring right here. We have all of our conjugated double bonds. And remember, because of that conjugated double bonds, we have a high amount of electron density in those areas. We have very electron-rich clouds above and below that benzene ring. When this reacts with an electrophile being something with a positive charge or possibly positive charge, right here, it's usually bound to something else. Usually it is a Lewis acid. What the reaction is going to end up doing is removing one of those hydrogens and putting the electrophile where that hydrogen was, and then the hydrogen is transferred to your Lewis acid. Okay, so in this case here, the electrophile is going to be interacting with the benzene, and then we're going to lose the hydrogen to regain aromaticity. Okay, so let's look at that mechanism and look at some specific reactions in that. We can take just benzene right here, and I'm going to draw the circle in the middle here, and if we react it with a halogen, for example, chlorine gas, we need to have an additive to the, remember, just adding bromine or chlorine to benzene does not react. We actually have to add a catalyst to the system. And in this catalyst, we're using the Lewis acid catalyst of Fe3. And what we'll end up doing is we're getting substitution of one of the chlorines is going to end up on the benzene ring, and the other chlorine is going to end up as the HCl salt. Okay, so using the same mechanism, we can use a different electrophile here. In this case, we're going to start with nitric acid, NO3, and we're going to have a catalytic amount or add sulfuric acid as the generator for getting us our electrophile, and we'll end up with a nitro substitution on that ring plus we're going to regenerate some acid right here, and it'll actually end up generating water. When we look at that same reaction, but instead of adding the nitric acid, we add SO2 with some strong acid like sulfuric acid to it, we can actually get sulfonation, where we end up with SO3H as our product here, plus water and acid. Or we can generate a positive charge on our carbon, and we can get what we can call alkylation. So we can have any R compound with something that can be removed from it, and we can get what we call Friedel-Crafts alkylation and adding of that R group. Or we can even do it with carbonyl compounds, for example, an acid chloride here, and we will get what we call Friedel-Crafts acylation because we're adding a carbonyl compound to the system. So we'll go over every single one of these reactions in this chapter, but they all have the same reaction mechanism. Okay, so it is a simple mechanism, but it starts with our benzene ring. And remember that our benzene ring here has those double bonds. Those double bonds are really electron rich. And so what we have is we generate somehow an electrophile that has either a positive charge or a partially positive charge, and that's typically bound to some kind of Lewis acid. The first step in this reaction is where the electrons from our double bond, from our benzene ring, reach out and take those electrons and make a new sigma bond to the electrophile. When we do that, we've changed the hybridization of that carbon. We have now a hydrogen here, we have our electrophile here, and we now have a positive charge on the benzene ring. Okay, notice we've changed the hybridization here. This is now sp3 hybridized right here. And of course, our carbocation is sp2 hybridized, but it has an empty p orbital. So what can happen now is that this positive charge can actually move around the ring because it's in conjugation. And so that positive charge can move around. So we have resonance structures possible. I'll just draw one of them here, and where we can have the positive charge here and our hydrogen and our electrophile. Anyway, so that positive charge is stabilized, moves around the ring until it tries to re-aromatize. And the easiest way for it to re-aromatize is to have it get that positive charge next to that sp2 hybridized, sp3 hybridized carbon right here. So we have our hydrogen here and our electrophile here, and we have our double bonds here. These electrons are then pulled in to re-aromatize the system, having the hydrogen leave as a positive charge, which is then reacts with the Lewis acid counter ion there. And so then we re-aromatize our ring, and now we have a hydrogen substituted by our electrophile. Okay. So each of these steps takes place in each of these reactions. The only difference is the creation of the electrophile. Okay, so let's look at the energy diagram of this to see how it goes from the starting material through that highly energetic transition state. So when we start out with our benzene in its low energy state as an aromatized material, and then we have our electrophile coming in and getting in close proximity to it. Then we have our initial transition state where we break aromaticity and we start to reach out with those electrons and grab that electrophile with the electrons in the benzene ring. That again changes our hybridization at that carbon to give us an sp3 hybridized carbon. And notice we now have a delocalized positive charge around the other 5 atoms in that ring. So the next transition state in here is having the Lewis acid come in and act as a Lewis base and start to pull that hydrogen away from the benzene ring. When it does that, the electrons that are making that sigma bond with hydrogen to the benzene ring are then pulled back into the ring to re-aromatize it, and we regenerate our aromatic ring plus our newly generated Lewis acid. Okay, so this mechanism is used for each and every one of the following reactions, and now I'm going to go into specifics in the next video about which reagents we use and which different groups we can add.